it. Okay. Okay, so good morning, everyone. Test, test, test. Not sure it's working. Test. Good. Test, test. I think. Can you hear me? And now? Okay, great. Thank you. So, good morning and welcome back to the lectures. Glad to see you all here. Yesterday we started discussing the first, the earliest part of this. Remember the scheme I showed you yesterday? I told you this represents the whole unfolding of the processing chain, where we have production of the multi-sensor data and then processing of such data to produce information which is intended for feeding the user's needs. Yesterday we saw the basic concept of remote sensing in the physical world. We saw something about how the physical measurements are translated into data and the features of the data that are generated by such translation. And today we will delve a little bit deeper into processing with for the time being, we'll limit ourselves to a layer of processing which is not intended for delivering the final information, but just for reworking the data in such a way that the information becomes more accessible. Okay? Then we will take one further step towards final production of information, focusing on one example, which I know best, which is medical representation. Okay, so determining what is located on your surface. So talking about that, let us spend a few more words about the data, because yesterday we discussed its, how can I say, its features, but I would like to give you some more clues about how the data actually looks, including some of the features that we touched yesterday, but we didn't discuss very, very deeply. Okay, so for example, one important point is data and metadata, in the sense that you may remember yesterday I showed you this scheme where I said we have two spatial dimensions. Okay. You can imagine them as a consequence of, on the one side, the physical advancement of the platform, and the other side, scanning of the use of multiple sensors. These joined devices will generate sweeping basically on the Earth's surface, which gives you two spatial coordinates. Actually, you may also remember that this is not north to south and this is not east to west. Right? So when the data is actually physically generated by the motion of the satellite, you don't get anything along the cardinal axis, because the orbit of a typical Earth observation satellite is zero. So between the data which is actually produced by the satellite and the data which is distributed to you when you download it from the portal that you saw yesterday, there's an intermediate step which is called geometric correction, which we will see later in this lecture, which is aimed at basically reprojecting this data into is oriented north to south and east to west for the convenience of the user. Okay, so the data that you download typically is not directly the data that was generated by the satellite, but it has been reworked a little bit to make it available in a grid where you can have the cardinal directions of the resultant analysis. Okay. Whereas the distinction of the spectral axis is still there, but is untouched. Okay. That is instead the subject of the processing, which is called the radiometric production. Anyway, whatever it may be, we have an array of measurements. The example of a figure that I usually use with my students is that of filing capital with so many drawers. Okay. In a typical, every drawer represents a pixel. Okay. So you can imagine this structure is something like this, where every drawer is associated with a pixel. And when you pull the drawer, you find numbers here. And these numbers I find this idea of representation very useful for students to make sense of what data actually means. Imagine you pull the drawer out of the cabinet and you find numbers on it, and these numbers are the spectral samples related with that piece. Okay, so if you want to know what is located here on your surface, on the part of your surface that was imaged by that pixel, you pull the drawer, you look at the numbers, and these numbers will tell you how the spectral reflectors curve goes. Okay, at least the samples that were acquired. By the way, let me make a connection with two other important concepts that I wanted to touch yesterday. When you pull the drawer and look at the numbers inside it, the sequence of those numbers provides you support spectral information. What is spectral information? It's the spectral behavior of the objects that were imaged. It's called spectral information because it's a behavior as a function of the wavelength, how the behavior of that object changes when you change the wavelength. It's called spectrum. Yesterday, we also briefly touched on a different type of information you can find hidden in these units. Do you remember what it was? Yes, you do. One is spectral information, and it regards one pixel. But if you broaden your view and you look at the surrounding pixels, what do you see? Sorry? Spatial, yes, spatial information. The information doesn't sit just on one single pixel. On one single pixel, you see the spectral information, which is an important piece of information. But if you broaden your view and you look at the surrounding pixels and you compare every pixel with the surrounding ones, where the neighborhood may be smaller, maybe big, depends on what you're searching for. But this is all spatial information. Okay. What you get is an idea of spatial patterns that are there in the image, which are useful to distinguish different, for example, different types of land cover, which spectrally look similar because they are, for example, soil vegetation. But I can distinguish one type of vegetation from another by the fact that there are slight changes between one pixel and the next, which I can only see if I look around, not just one pixel. That is spatial information. Okay. And this seems like a philosophical distinction, but it's very important in practical terms. Because what spectral information can tell you, what spatial information can tell you are different things. When you work with spectral information, you get information about that specific, about the chemical composition of that specific object. But if you want to learn something about, for example, homogeneous versus inhomogeneous Van types, like the example of the medias that I could make others. Like for example, the distinction between regular plantations rather than natural vegetation. This is also a matter of spatial information rather than spectral information. So depending on what you want to do, if it has to do with spatial patterns, most likely if it has a reflection, if your goal information has a reflection on spatial pattern, then most likely you will need spatial information rather than spectral. If you want to know, if you want to identify a pollutant agent, most likely you're not after spatial information, but rather spectral information. Because a pollutant agent will leave a mark on the spectral response of the affected pieces. Okay. Are you with me? Now, I discussed a lot on this image, but the original intent here was a little bit different. I wanted to, I mean, it was important to wrap up this discussion to clarify the difference between spectral and spatial, but also the purpose for which you can leverage these two information. Now, back to the original goal of this slide. When you download data, like when you access the Copernicus portal and you decide, I want to download this and I get this 800 megabytes of data, okay, most of these 800 megabytes of data, let's say 750 megabytes or even more, are composed of the actual remotely sensitive data. So you have big multi-level arrays like this, where yeah, you basically have measurements. Okay, but in order for you to be able to make sense of this data, you also need to consider the additional piece of data that comes with this, with the measurements, which is called meter data. It's much smaller, but it must travel hand in hand with the data because it's basically the descriptor of the data. That is necessary in order for you to have a correct understanding of this data. This is something that happens even, for example, for JPEG representation of images. Okay, if you have an image, a JPEG image, and it's 75 kilobytes, these 75 kilobytes are not all pixels. Okay, a large part of it are pixels, but then others are, for example, the size of the image or the quantization of the coefficients that are used for representing the JPEG image, etc., etc. And if you don't have this small pixel, it's a small piece of information, you cannot interpret the rest. And something similar happens here. Okay. It is important to remember this because frequently a remotely sensitive data set do not come as a single piece. They can come in multiple parts, one of which is the data set. Then you have multiple other files which seem to be not so useful, but actually you should keep them because of this. Okay? And always have in mind that basically this is the key to reading this data. Okay. This arrangement of data in the form of matrices with rows and columns is a natural consequence of the way the data is acquired. Okay? Samples arranged in horizontal and vertical rows. That's called raster format. I think this is something that you already heard of. raster. Um, we call it raster because in geospatial processing, you frequently have to do with another type of data, which is called vector data. Okay. Remote sensing data typically comes in support raster format, but we also have a support vector format, which is other sources of data which are not remote sensing data, but are still important for your purposes. So, like, for example, if we go back to the original scheme here, okay, the main one is that we have remote sensing data here, but we also have this box here, which is the reference data. This reference data doesn't come from the sensor, it comes from elsewhere, unspecified, unspecified because it can be many different things. Typically, these are additional pieces of data that help you interpret the remote sensing data set. Like, for example, they can come in the form of maps that are generated by other means than remote sensing. For example, by on-site inspection or by archival or, like, for example, cadastral data or other forms of data that do not originate from this sensor, but nonetheless are very useful to be integrated in the process. Why? Because, for example, if you know that if you're thinking about a city, or you're thinking about agricultural land, on which you want to do some processing, like, for example, you want to assess which crops are grown where. The task is easier if you know the boundaries of each field. So you don't have to fight against the problem of distinguishing where one field ends and the next one starts. If you know from other sources that this is the extent of the field, and most likely all these pixels contained in this field are on the same plot, then you can more effectively cancel the error which is naturally superimposed on your readings. Okay. So I know this is all the same plot. I don't know what plot it is, but I know it's all the same plot. So I know that if the readings are different, I can, for example, do what I should do, still effective like averaging the readings, because I know I'm averaging homogeneous samples. I don't know what I'm searching for. I know what I'm searching for. But I know it all should look the same, so the differences are going to be errors. So if the reference data suggests me something like this, it can facilitate my processing. Okay. So what is vector data? I talked about OpenStreetMap with some of you yesterday. OpenStreetMap is a source of vector data, which is typically used in the context of Earth observation for sourcing reference data. Okay. So take into account this OpenStreetMap.org. If you are in need of reference data for your data set, yes, one more example from the discussion yesterday. One more example of why reference data is important. Reference data is very important for another purpose, which is that of tuning your algorithms. If you're searching for something and you know where examples of that instance are located, the big problems, one of the big problems in Earth observation data processing is exactly the lack of reference data. If you're if you're seeking to classify a certain type of crop, identify a certain type of crop, typically you will need examples of how that crop looks like in the type of data that you are using. Okay, there's no universal solution. Even if you have typical spectral response of that crop, which comes from time, it's still frequently not enough because you don't need the general behavior of that crop, of that length type. You need to know exactly how that translates into your data set. Okay, to the data set that you are using. Theoretically, it's easy. It should project in a straightforward manner, but it's never like that. Okay, so the most effective way of approaching the problem of tuning the algorithm, it applies not only to deep learning or machine learning approaches, but also to the classical ones. Okay. You always have to tune some way or the other the algorithm that you're using to identify that relevant type of surface cover in specific type of data that you are using. And the reference data is a typical source for that type of information. OpenStreetMap, I used it here to illustrate the concept of vector data, but it's actually a practical source which you can address to in order to see whether the data that you're interested in can be found there. The example here was from the urban applications, and this is my group now. I used it to illustrate that I like remotely sensitive data, which features a inherent resolution. Okay, so for example, Sentinel-2 data, which we saw yesterday, we didn't download it, but we saw it. It gives you pixels that are sized 10 times 10 pixels, highest resolution. So that's 10, that's it. If you zoom in, you just get bigger pixels. But in the case of vector data, you have no predefined resolution. So as far as there's information in the repository, you can zoom in to the extent that, for example, you can distinguish the individual building in this case, or the individual field. Or if there's sufficient information, you can even distinguish in the boundary of the field where the field ends, and then when the next field starts, and that's no one is laying. This is typical of vector data, and most environments, most geospatial data processing environment can understand both types of data and handle them at a time, and convert one type of data into the other. Okay. We don't have much time to go into the details of this, but please be aware that we have these two words that coexist in Earth observation data processing. Raster because of Earth observation data generation, and vector because of data from other origins, like in a field you describe the corners, and that's the description, that's the vector description of the field. The rest of the information comes as a new sequence. Okay. Now, I don't think I need to pass the book in this. Is everything clear so far? Did I say anything new with respect to what you do? In Earth observation, this is quite basic, so I don't want to think it was useful to make up our minds about, especially if you don't have practical experience about Earth observation. I think this is useful to make sense of these. Yeah.
Sir, this raster data somehow changes the communication and sync of already existing last slide.
You mean,
Go back to last.
yeah, yeah. This one, yeah.
So this raster data on top, we can see there are some distortion.
Yes, definitely. I mean, when you use together the same environment, raster and vector data, and frequently you have to, because there's no other choice. There's always distortion. We can call it distortion, or we can call it error, or quantization error. Any of you has a background in signal processing, you may understand the expression quantization error. With vector data, you can be almost infinitely precise about the location of the object because you're not bound to be either in one pixel or in the next pixel. You can describe exactly the location of the object. Okay. So, in this case, I have the location of Wales. It's described by its coordinates. Okay. It's not a matter of selecting one pixel or the other. It's okay. The object is located exactly here. So that's the reason why in this arrangement I have theoretically infinite possibility. As long as I can add decimals to the position, I can further specify the location of the object. Okay. But when I have to do with vector, sorry, with raster data, I'm forced to place the object either in one slot or in the next one, or in each one. It's quantized. Okay, so there's no third way in between, either here or there. So this leads to the generation of an error when I have to forward vector data into raster data. Because if it's in between, I have to make a choice. And if I put it here, I'm making this error, I'm adding this error. If I put it here, I'm adding this error. And there's no way to make it zero. Okay. So, yes, definitely, when I mix vector and raster data, I'm adding errors to the data, I'm adding noise to the process. But most frequently, the advantages of merging information overlaps the disadvantage of adding error. Okay. So it's fine to do, and it's commonly done. Yeah. Now, why I was and let me add one thing. Even when you remember this, even when this is the swap, this is the swap, and this is the arrangement of tiles. But actually, this is how it works with Sentinel. Basically, what I do is I split the Earth surface into a regular grid with arrangements also to take into account the round shape, the spherical shape of the Earth. It's quite a complicated sort of. I myself I don't exactly know 100% of how it is, but still, in a local context, you can be sure that the result of this operation is that when you take the so-called tile, 100 kilometers times 100 kilometers, it's being reworked to be oriented north to south and east to west, okay, which is very useful for handling the data in a practical way. But this is the result of taking small of satellite and reprojecting it, projecting every single pixel into a location within this regular north to south, east to west grid. This process is called grid sampling. And grid sampling also involves network. Okay. This is one more thing we take into account. When we download data from the portal, we don't download the original data. Those data are not accessible in most cases. In some they are, especially for greater data because they can be used for some types of processing. But in the case of Sentinel-2, you don't access the layer behind this. You access the tile, and the data in the tile has already been reprocessed. So to place, so to move the pixels from one grid to another. Naturally, if you have one grid with a certain tilt angle, and you have to take those data and rearrange them in a regular grid which has a different orientation, you cannot do that exactly. You cannot do that exactly. Okay, think of two grids, one at an angle with respect to the other. There's no way you can match them. Okay. So there's a process called resampling, which follows certain criteria, which tries to minimize the error according to a certain criteria when you pass the data from the original swap to this regular grid. It will minimize the error, but you cannot cancel it. Okay. So when you get these data, you already have data with an additional error due to this process. Mind that it's impossible to keep the errors. Okay? You can never get to kill the errors. What you can do is you can minimize them, but you will never kill them. When the original measurement is subject to error, like any other measurement in the world, it's never perfect. It has an error. What you need to do is to try and avoid building more errors on top of that. But in most cases, it is justified. So this process generates additional errors. If you combine this data with vector data, you generate additional errors. And this mount up. One of the things that you need to take care of, this is important. So sometimes I see it is overlooked, but it's very important. When every time you work with the data, every time you rework the data, every time you project the data, whatever, you add a little bit of error. Okay, remember that. Be aware of this. Okay. So, what you download here has this additional bit of error. But still, once more, the convenience of having data in a regular grid is greater than, is a greater advantage than the small amount of additional error that you introduce in this case. Another concept that I briefly touched on yesterday, but without explaining it too much, is the concept of data levels. Let me see. Sorry?
Grid reason. Grid reason.
Grid resampling, yes, grid resampling, right.
But in grid resampling, we definitely know what is the orientation and how much angle
Yes.
the data is.
Yes, yeah, you know the orientation, you know everything. I mean, you have all the input data. But then the problem is when you have the pixel on the new grid, that area is not matched exactly by any of the previous pixels. So you're in a situation where the new pixel always contains contributions from more than one pixel from the previous grid. Okay. So there are various strategies that you can implement. You can decide that whichever pixel covers the most, then I will use that, ignoring the others. That's an error. Or I can decide I interpolate, but as you know, interpolation doesn't mean finding a correct value. Interpolation means trying to guess the best of your possibility value. There are more complicated approaches, like you can define you can consider more pixels and consider the local interpolating spline or a polygon, polynomial of a certain degree, etc. There are various ways you can do that, but you can never find the correct value for that pixel. It's always an approximation. And the difference between the ideal value and the approximation with which you come up is the error you're adding on top of your data.
How many such small grid in one grid? How many such small transitions? How many such small pixels
Generally 4. Most likely 4 in some cases. This is quite easy to see. If you imagine trying to fit one grid into the other, in most cases, one slot from one grid will cover 4 slots from the other grid to various degrees, but the number is generally 4. Okay, let me show you one thing. Because I probably I was, yeah, it's probably here. Yes. Before talking about the levels, let me tell you something about data correction, which I believe is relevant to you. I briefly mentioned that the data we consider either those 2 main correction steps, one being arithmetic correction, the other one geometric correction. Now we discussed geometric correction. One thing that focused mostly was on the projection between the grid generated by satellite motion and the grid that we would like to use for precisely investing. That's one part of the problem. There are other parts of the problem, a geometric problem, which is not just the orientation, but also the fact that the Earth rotates while the image, so you have additional distortion, not just the angle, but also the shape. But one more important component is the geometry of acquisition. So the fact that, first of all, the satellite may be looking straight down, which is the general case, but it may also be looking at an angle here, which generates foreshortening distortion that needs to be corrected. But even for near looking satellites like Sentinel, okay, you have first of all you have the fact that you're looking straight down only on one line, but all the other lines are at an angle. So think of it. Yesterday I mentioned that the swap rate of Sentinel is 2 300 kilometers is not matched with respect to 600. Okay, so you're not looking straight down. You're looking straight down at the center of the seat, and you're looking at an side, so you're generating a perspective, which needs to be correct. Okay. One more element is the fact that you're looking at perfect speed. Locally, you're not looking at a perfect plane. You may be looking at a perfectly flat area, but that's an exception. The rule is your changes in elevation locally. That adds to the geometric distortion, which is involved in your data. So when you acquire the data from the satellite, you project it down to the Earth, assign locations to the various pixels. You need to do this geometric progression, which is a little bit more complicated, but they're skimmed over it because it's all the subject of the course. But I want you to be aware of that. The data which is generated by the satellite is not ready for use, not at all. You have to, first of all, implement the so-called geometric correction, which basically places all the data samples in their correct location. And that's not easy, not at all. Okay. So this is matter for experts of that operation. So generally, geometric correction is done by the data producer themselves. And the data, the type of data that you get is already corrected. You may want to be aware of what happens to the data if you want to do particular types of processing for which residual errors, for example, may be relevant, like if you want to locate exactly a certain object or whatever, then you may need to know the details of the correction step. But in the general case, you're usually happy knowing that the geometric correction step was done correctly. Okay, so I won't go into the details of it, because I wanted to move to the other type of correction, which is called radiometric correction. So in the earlier one, we corrected pixel rotations. In this case, we corrected pixel values. What is the idea here for radiometric correction? Is the fact that when the sensor looks down at a certain object, the ideal situation is I have a certain well-known amount of radiation that lands on the target. The target reflects some of it in intercept, but remember, you already heard the story. The target reflects a part of the radiation which then goes to the sensors for being recorded. But actually, in the real world, the situation is far more complicated because there's the atmosphere in between, and unless the goal of your observation is exactly the atmosphere, whatever change the atmosphere causes in the density of radiation you do, it's an error. Right? So you have to estimate such error and correct it. This process is called radiometric correction. And there's a series of steps involved. We won't go into the details of them. But again, be aware of that. This is a critical process. It may seem nothing, but you need a lot of information to be placed in the process for you to get to a decent result of at surface reflectors. So a number that tells you how much of the incoming radiation was reflected, the percentage. Okay. But getting here, starting from the data that you get from the satellite mounted sensor, is a long and bumpy path. This is another truth that we say about Earth observation data. The data that you get from the satellite mounted sensor is far from there's a number of errors that needs to be removed one after the other before you get to the final correct destination. And let me point out this costly process. Remember yesterday I said not all of the data is available at level 2. Why? Because the process is so big in terms of input data and in terms of processing cost. Not all of these operations may be always the same. So if you want to use a very robust approach to information extraction from remote sensing data like your own eyes, well, it's not that much. This is Venice with a visual rendition of the uncorrected and corrected data. Probably you can see it better here because the image is not very good quality. But if you look here, you will see the difference between the uncorrected and corrected data. Visually, you can still see, for example, where the sea is and where the solid land is. You can even distinguish probably the largest buildings. So if your application is count the largest buildings, you may be happy with uncorrected data, but that's rarely the case. In most cases, you need to correct the data and see. And what is the visual difference between the two halves of the image? Sorry? The clarity, yeah. What is found here which you don't see here? Sort of haze, right? That haze is the visual rendition of a measurement error. Okay, what is this measurement error? It's radiation that the sensor is measuring from the scene, but it actually doesn't come from the scene itself. It comes from the atmosphere. Why? Well, because the atmosphere is adding its own radiation on top of whatever the satellite is recording from the scene itself. So if you do a correction step, then you will see that visually the haze will disappear. But this is just a visual rendition of a physical fact. I estimated how much radiation came from the haze and I subtracted it. Okay. Now we can get back to the previous presentation because sorry? Yes. One of the two sides of the image, the left side of the image was level 1C, and the right side of the image was level 2A. So in one case, it was not yet corrected. In the other case, it was corrected. Radiometrically corrected. So that brings us back to the previous presentation where I said data levels. We only saw two examples, but you can see there's a long path between the data, the raw data generated by the satellite, and the fully corrected data that you download to use in your processing. And lower levels, right? Level 0 and level 1, level 1B data, etc., are not generally distributed because they are so much affected by errors that you may not be interested in them. So you leave the data producer to do their job and raise the data to a level which is generally usable by general user. Okay, which in the case of Sentinel-2 is level 1C, Then the concept of level of data extends to further up, where you have so-called variables mapped. In this sense, in level 3 or level 4, there are various levels up here, depending on the distance that you, on the ideal distance that you put between the original data and the information that you derive from that. So, like for example, well, you saw level 2A data yesterday. Level 3 data variables now could be, for example, the density of vegetation. Okay, that's how remote sensor data and it's an estimation of a biophysical variable done based on data. It generally has the same form. So you have a raster here, a raster layer of remote sensor data from which, applying a suitable algorithm to each of the pixels, you get a raster layer of estimated vegetation density, okay, or estimated biomass, or estimated soil humidity, whatever. Basic physical variables derived from the data. Then from those variables, you can derive more refined ones, like, for example, based on biomass, you can derive yield estimation or other more complex variables and so on. So this is the concept of data level, and it was originated by NISA in the 80s when they were when processing of the Landsat data was taken down in order to have a common reference between the scientists which were working there, which were learning how to work with this type of data. And it was found convenient and it's still adopted and it became official. So remember about this reason, what level of data you're working on. So it's not all data, not all types of reconciliation data created equal. You may work at different levels depending on what type of data you need.
Yesterday, we have also seen L1C and L2C.
Yes.
So these two are provided by the data provider.
Yes.
I want to ask, like, on level 2A to get from 1C, they have radiometric
Correction. Yes.
So whether it is the best radiometric corrected algorithm they have implemented?
It's not necessarily so it's probably the best. It depends on the definition of best, because if you don't have reference data at the time of acquisition, like for example, if you don't have a so-called calibrated target, you don't really know whether that algorithm is performing better than another one. They did a calibration campaign at the beginning where they had some targets with known reflectance, and so they tuned the algorithm. They decided based on the scientific methods which algorithms could perform best, and they did at the beginning, like for any other Earth observation system, they performed a so-called calibration campaign at the beginning where they used reference data to tune the algorithms and their parameters in order to do as well as they could data from level 1C to level 2A. Okay. So we could say that in the general case, this job is quite well done. Okay. Nonetheless, you may not be happy with that type of correction because it's good for everyone, but possibly except your specific application. Because you have particular requirements in terms of precision and accuracy you may not be happy with that. You may want to do your own correction. That is the other reason why level 1 C data is available. So, no question. That is why level 1 C data is available, because you may want to do your own correction. And there are additional plugins that can be paid to the standard data processing environment, which is called SNAP, European Space Agency. One is called SEN2COR, SEN2COR, which is designed to do exactly this, to bring level 1 C to level 2 D. It does the job using your own input data. So you want very precise, very accurate, very everything data in your study area of interest. Now, you need to get reference data on that area, otherwise you're doing worse, not better. Okay. So you install local sensors, for example, a sun spectrometer, a sensor of atmospheric scattering, well, all the suite of sensors that lets you describe the atmosphere to the level of accuracy that you need. And then you take this data, you put that, you take level 1 C data, you take this data, you put them into the algorithm, and you get a better correction than the standard one offered by the ESA. Okay. But you need to have good reasons to do that, because it's very expensive and time consuming. Okay. So in the general case, you're happy with level 2 input. If you have special requirements, then you step back one level, you generate your own correction data, and you do that yourself. It's feasible. Okay. But you may not be interested in doing this type of correction. This is really nasty. So it's left to be SEN, SEN2COR. SEN, SEN2COR. There's another one that I don't remember the name now. I think there's a Python version of it. There's a Python version of this. It's open source, so it's usable by anyone. I think I overdubbed this lecture, so let's take a break. It's 11:30 to 11:40 was supposed to be a break. Maybe we can reconvene here, not at 11:45, because it's in a couple of minutes. Sorry for this, I didn't realize that. My apologies. We can reconvene at 10 to 12, if it's okay for you. Approximately 10 to 12. Okay. I won't scold you if you're not back exactly on the beat. That was me, probably. Thank you.